I'm going to do it this way, like Dr. Phillips, because like her, I have a cold also. And I don't want to cough into a microphone. Anyway, this is about the Ice Age, but it's taken it further on what can be considered catastrophic models for other aspects. And they might not necessarily be catastrophic, but they're interesting offshoots from the Ice Age. So let's do a little review. This is the general Ice Age model. Warm oceans caused by pre-flood warm oceans, and then lots of volcanism and fountains of the great deep, hydrothermal flow. So you can end up with a warm ocean, pole to pole, top to bottom, and the significance of that is you evaporate a lot more water into the air with the warmer the water, and especially be significant at high and mid latitudes, with a lot of reflection of from the particles in the stratosphere as well as the top of the clouds, ending up with a rapid ice age. So that's kind of a quick, easy schematic on the Ice Age. And then to time it, I had to assume what kind of temperature we started off with at the end of the flood. And someone asked me a question of this, of why. Well, it's because the pre-flood ocean would start pretty warm. And if you're adding all this heat from lava flows, it's going to be even warmer. The pre-flood ocean was warm because, based on the amount of coal, we had at least 10 times the amount of vegetation and trees on the continents before the flood as now. And trees give off water vapor, transpiration, and that would cause a pretty strong greenhouse effect before the flood. Water vapor is about 80% of the greenhouse effect, by the way. In fact, the greenhouse effect is good. Without it, we'd be 60 to 65 degrees Fahrenheit colder, and we'd all freeze to death without the greenhouse effect. It's a good thing, not a bad thing. Anyway, I assumed that the Ice Age ended before the oceans cooled to the present temperature of 4 degrees centigrade. So I assumed 10 degrees where it came to a maximum. And then it melted, but the temperature still cooled off. I'll be getting into this a little more, even more so than the average temperature of the ocean today. And then I recently drew these. These are estimates based on basic meteorology. Cooler summers based because of all the volcanic particles in the stratosphere, and warmer winters caused by all the warm water. They're going to have quite an influence in winter, especially winter, because you give off you have more storms in winter, you give off more latent heat, you heat the atmosphere more. So there's reasons why you'd have little seasonal contrast right at the beginning of the Ice Age. But as time goes on, we get less particles in the stratosphere, the sun becomes more powerful, and you finally rise up to what we have today. But the winters become colder and colder, and even colder than today. And I'll give reasons why that is the case as I get into this presentation. Precipitation with warm water, a lot more evaporation. You're going to have heavy precipitation globally. This general circulation would probably be quite different than today also. Now, I haven't figured out what that would be, but regardless, there's going to be a lot more water vapor in the air. So even in areas not glaciated, you're going to have heavy precipitation. But as time goes on, it actually dries out more and more, and I'll get into why that's the case. Then, during the Ice Age, we have the rapid buildup of Greenland and Antarctic ice sheets. It builds up pretty fast during the Ice Age, which maxed at 500 years, but it continued building because you still have a lot of warm water around, and Greenland and Antarctica are at high latitudes and by this time high elevations. So they would continue to grow, but they eventually reach a steady state, which we're in right now. And of course, you might wonder, how can we have such high precipitation? It can be 6 meters a year early in the ice age over Greenland, and maybe 10 meters of this is ice equivalent over Antarctica. Well, there are some analogs. These are imperfect analogs. This is in northwest Japan. They get a huge amount of snow. This is about 4 or 5 months worth. But in Antarctica and Greenland, you'd have it collecting for 12 months. And the water being warmer, it'd have more moisture, and so you'd have even much more than this analog right here. So you can have rapid precipitation early in the ice age. Okay, let's get into the topics. That's just kind of an overview of ice cores that I talked about before in the ice age. We're going to talk about catastrophes. Well, they discovered that there's catastrophic ice age floods. For example, the Lake Missoula flood. Number 2, there's a lot of mysteries associated with the ice age, which you could consider catastrophes. I'm going to only talk about 5 of them. And I'm going to give reasons why there's no post-flood catastrophes. And I realize I'm getting into controversial ground here. And I recognize that. Anyway, this is the Lake Missoula flood. A finger of the ice sheet developed in northern Idaho, blocked the Clark Fork River, created a lake 2,000 feet deep, 600 meters deep at the Idaho-Montana border. By the way, I live just around in here. And it filled up a lake that was about 5 times the volume of Lake Erie. And of course, it was held by ice. And it's not going to last like that much, because this was likely increasing year by year as the glaciers were starting to melt, or the ice sheets. And then here's Glacial Lake Columbia. So what happened is it broke through here and filled up Glacial Lake Columbia, and it spilled over a ridge going down that way through eastern Washington, carving up, eroding 50 cubic miles of hard basalt and soft silt. Just one regional flood, 50 cubic miles. What's that in cubic kilometers? About 250 cubic kilometers. Anyway, that's the Lake Missoula flood. And from space, you see the path. It's about 100-mile wide, and it kind of diverged around, and there's some main paths like the Cheney-Palouse tract and through Grand Coulee. And you can see the shorelines from Glacial Lake Missoula all through where the lake used to be in western Montana. This is one famous example across from the University of Montana at Missoula. Really distinct wave-cut shorelines. These shorelines are cut in both hard and soft rocks, by the way, the same. And then you go north, the lake was in here about 1,000, a little more than 1,000 feet, 300 meters deep. And as the ice broke, it came over this ridge and accelerated down slope, moving, they think, 60 miles an hour, forming these ridges, which when you drive across there's a road that goes across there. You can't tell what they are, but from space you see the ripple marks. Now these ripple marks are about 40 feet tall of gravel. They're gravel ripple marks. So, and then it cut Grand Coulee, which and basalt lava 900 feet deep, leaving an erosional remnant up here in a matter of 1 day. That's the Lake Missoula flood. And it formed what are a bunch of dry waterfalls. J. Harlan Bretz, who I consider quite a geological detective, was looking at these sorts of things and realizing that this is a dry waterfall. A normal drainage, given enough time, would erase that waterfall. And there's deep plunge pools down in here. And there's another spot very similar to that. Before going over a ridge before the Columbia River. It formed these what's called the potholes. Very scenic around here, eroding the basalt back from the Columbia River about 2 miles, 3 kilometers, and forming these plunge pools, which in the summer collect a lot of algae and turn green. It's very scenic around there. And of course, you find all these gravel bars, about 100 of them, out in the middle of nowhere. This is southwest of Spokane, Washington. And I might add that when the ice broke, it moved over the current location of Spokane, Washington, 600 feet deep. And through the Columbia Gorge between Washington and Oregon, it was 1,000 feet deep. We know this because of they carried icebergs with erratic boulders, and by the altitude of these erratic boulders, we know how deep it was. When it spread out in the Portland, Vancouver area, it fanned out and it dropped a load of gravel, forming another gravel bar that is 300 feet deep, 200 square miles. By the way, if I use miles and feet, do you understand that? Because I can translate it into kilometers, and sometimes not quickly. But anyway, this is gravel, 200 square miles, 300 feet deep. And by gravel, I mean big boulders. And I believed it was going through the Columbia Gorge 80 miles an hour. And after it deposited this bar, it then channelized and cut right through it. And you see all these rocks ripped out. This is basalt that's ripped out from Lower Grand Coulee, which you can't see in the background. It's been moved at least 5 miles. And then here's a granite erratic on a ridge above the Columbia River, left on a ridge by iceberg. These icebergs carried all kinds of rocks in them and deposited these erratic boulders clear through the path. And I showed you this one earlier. This is southwest of Portland, Oregon. This is argillite, which is slightly metamorphic shale. This kind of rock does not outcrop in the whole state of Oregon. And this is the type of rock you find in western Montana and northern Idaho. So it's been carried by an iceberg that far in the Lake Missoula flood. So there's hundreds of pieces of evidence for the Lake Missoula flood. And J. Harlan Bretz, when he first he published a lot of this stuff in the Journal of Geology and so forth, and no one believed him except possibly one guy, J.D. Pardee, who did his research in western Montana. And it didn't help his case that he didn't know where the water came from. He just said that the evidence from geomorphology is a huge flood here. But 10 years later, he figured out where the water came from. Now, this Lake Missoula flood was rejected for 40 years. And a lot of people have made statements, well, why? Because it was too biblical in scale. Few have actually admitted that, too biblical in scale. So based on that and that bias they have, I don't really expect too many uniformitarian scientists to really see evidence of the runoff of the floodwaters on the surface of the earth. But we learned from the Genesis flood, about the Genesis flood from the Lake Missoula flood. We can use that as an analog. And what do we discover? Well, it produced erosional remnants. Vertical towers like Devil's Tower. And there's thousands of these across the earth, indicating that a huge amount of water ran off. And water and wind gaps. A water gap is essentially a gorge through a mountain range or a ridge or a plateau. A wind gap is like a water gap, but it's not carved deep enough. These formed during the Lake Missoula flood that was carving up eastern Washington. And we find these water and wind gaps by the thousands across the earth. There are 1,700 water gaps in the Appalachian Mountains alone. And the interesting thing about water gaps is that if it was the river that formed them somehow, which they don't often believe, but sometimes that's all they got. The river should have went around, but a lot of times it didn't and cut right through it, the ridge. And it's an analog for a rapid deposition of the continental shelf and subsequent submarine canyon formation. For instance, I showed you this slide. An analog for the formation of the continental shelf would be when you have wide currents spreading off the continents. They'll form a layer of sediment, forming the continental shelf and the continental slope. And then when it's all over with, the water is channelized and ends up accelerating and carving canyons through the continental shelf. So this would be an analog of that. This gravel bar here is called the Portland Delta. So they finally accepted the Lake Missoula flood in the 1960s based on aerial photos. They found ripple marks, about 100 ripple marks on gravel bars, and from the space you saw the path. But since then, they've discovered about 40 other Ice Age floods. 40 of them about. Victor Baker has written a paper about this, so this is well accepted now, and so they see these catastrophic processes associated with the flood. Also, the Ice Age presents a solution for 5 mysteries. 5 mysteries. What are they? Well, here's 5 of them. Why are woolly mammoths by the millions in the far north? Siberia, Alaska. Also, why were the lowlands of Siberia and Alaska unglaciated? Also, desert areas, now arid areas, including Australia, were wet at one time and have evidence of large lakes, shorelines associated with those lakes, flowing rivers. Also, a 4th thing, they find that the animals and plants of the Ice Age were from different environments. They were animals that loved the warmth next to animals that loved the cold. And this is not an exception, this is the rule during the Ice Age. And at the end of the Ice Age, mainly their last Ice Age, there was a gigantic mass extinction of mammals over 100 pounds. So here's the woolly mammoth, very distinctive. It has there's another type of mammoth that mainly lived in southern United States called the Columbian mammoth, and you have equivalents in Europe. And you find woolly mammoths, but the experts that work on the bones in Russia, Siberia, estimate there are millions of these in the permafrost. They're not in glacial ice, they're in permafrost, but that permafrost has a lot of ice in it, ice wedges and ice lenses. So that's probably what gave the rumor that they were in glacial ice. Anyway, here's the woolly mammoth distribution, the red area, all across the northern hemisphere, except we're in the central and northern parts of where the ice sheet occurred. Now, it's interesting that in some places they're juxtaposed within the boundary of the ice sheet, which brings up some interesting scenarios, which means they were there either before it glaciated or after. But anyway, this is a major mystery of Earth science, is why the mammoth disappeared from the Earth. And this question remains one of the great unsolved mysteries of the past. It's been around for almost 200 years. Why? First of all, why would they live in Siberia and Alaska during the Ice Age? Secondly, what would they eat? And third, how did they die? Anyway, I'm not going to get into those, but this Ice Age model that I've worked on can account for that. And when I talk about the lowlands of Siberia and Alaska, I'll give even more evidence for that. But the second main mystery is the lowlands of Siberia and Alaska were unglaciated. And here is a schematic of that, where the mountains were mainly glaciated. This pattern right here, the yellow area, they were not. And why was that? You know, they run these climate models, and they try to get glaciation, but it's pretty hard to get glaciation. Sometimes you got to force it. One model decreased the solar constant by 6%. That's a 6% drop in the sunlight. And then they got glaciation, but unfortunately it was in the wrong areas. And this is another study from climate dynamics. In particular, most models tend to simulate a net accumulation of snow over northern Siberia, the Chukota Peninsula, and Alaska, rather than over northeast Canada, Quebec, and Scandinavia, where ice sheets are believed to have first appeared during the last glacial inception. At the same time, most models either underestimate the rate of initial growth of ice sheets or place them in apparently wrong places. So, the lowlands of Siberia and Alaska are great areas that should have been glaciated, but they weren't. Well, why was that? Well, I think it's because of the warm water, especially the warm water. A guy did a computer study, and he just took off the sea ice of the Arctic Ocean and left the temperature at the freezing point of seawater, which is about 28 degrees Fahrenheit or about -3 degrees centigrade. And he compared the winter temperatures today versus what the winter temperatures would be like without the sea ice. And this is in degrees centigrade, by the way. So over the North Pole, it was 40 degrees centigrade warmer in the wintertime. And in northern Siberia, it was about 20 degrees centigrade warmer. So that would add a lot of warmth in the winter with no sea ice to Siberia and Alaska. And there's something called onshore flow, where that warm air would constantly bathe Alaska and Siberia, keeping those areas warmer in the winter, but causing heavy precipitation in the mountains. Wet deserts. Well, the Great Basin in the United States is an large enclosed basin. And here are the current lakes in there, like Great Salt Lake in Utah. It's about an average of 12 feet deep. 12 feet deep. But during the Ice Age, you had a huge lake there that was about 800 to 1,000 feet deep and about 8 times the size of the Great Salt Lake. And you had a lot of other lakes during the Ice Age, all through here, even in Death Valley, the hottest place on Earth. And here's Glacial Lake Missoula. Now, this Lake Bonneville, they call it Lake Bonneville, it rose. We know that because it overtopped a pass and then caused a flood down the Snake River called the Bonneville Flood, and it lowered that pass about 100 meters. So here are some shorelines associated with Lake Bonneville. Several levels of shorelines. The highest it got up to this point right here, and that's when it overspilled and probably dropped 100 meters down to this level right here, and finally evaporated. And here is shorelines in Death Valley, right in here. So you had a lot of lakes in the southwest United States. Also, it's well known that Sahara Desert was well watered during the Ice Age, as well as Saudi Arabia. They find fossils of aquatic organisms like hippos, and man's art is in the Sahara by a couple thousand pieces of art. Also, the Dead Sea was believed to be maybe 1,000 feet deep at the start of the Ice Age, based on some shorelines. And they keep moving these shorelines up more, but I don't know how solid that is, but you had a pretty good lake in the Dead Sea area of Israel. And here's some of the pictographs in Africa. There are thousands of these in Africa. So it was well watered, big lakes in the Sahara, and in other places that are now dry. And the reason for that, of course, is because the general circulation was a lot different. There's a lot more moisture in the air. The fifth major Ice Age mystery, fourth, is disharmonious associations. Anyway, here's a quote from a book called Quaternary Extinctions of Prehistoric Revolution. They're the rule. Late Pleistocene communities were characterized by the coexistence of species that today are allopatric, meaning not climatically associated, and presumably ecologically incompatible. Disharmonious associations have been documented for late Pleistocene Ice Age floras, terrestrial invertebrates, lower invertebrates, birds, and mammals. In other words, it's the rule and not the exception. And it further pointed out in the literature that this implies an equitable, mild, equitable climate, exactly what we'd expect early in the Ice Age. But some think that, well, maybe there is higher tolerance for some of these animals, but research has shown that the higher tolerance doesn't quite work. I'll give you an example. And sometimes they try to separate these animals to a glacial environment for your woolly mammoth and an interglacial mammals for their interglacials. Try to separate them, but that's difficult. For instance, in England, there are at least 100 locations where you have hippo fossils from the Ice Age. Can you imagine that? Hippos. And they're also in France and Germany. So they're in Northwest Europe, but England has over 100 of these. And hippos today are found in this region today, at least historically, the red area. The green area, I think, is the current distribution. Anyway, Don Grayson said in that book, in the Valley of the Thames, that's southern England, for instance, woolly mammoth, woolly rhinoceros, musk ox, reindeer, hippopotamus, and cave lion had all been found by 1855 in stratigraphic contexts that seemed to indicate contemporaneity. In other words, they're found together. You really can't separate them like they want to do. And they even have another problem. There weren't any previous interglacials, as I will mention here soon. And here's another more recent, well, no, that's not more recent, but anyway, another quote: finding conditions so favorable for the hippopotamus, today an inhabitant of the equatorial regions, had been able to spread northwards through most of England and Wales up to an altitude of 400 meters on the now bleak Yorkshire moors. That's in central or northern England. So how would that be explained? Hippos, well, here's how I would explain it. When you have warm North Atlantic waters, you're getting onshore flow into the United Kingdom. So United Kingdom's going to have pretty warm winters, lots of precipitation, because the warmer the air, the more water vapor it holds. And so it'd be a great environment for hippos right after the flood. But the flood was a very dynamic climate, and winters became colder and colder, and finally the Ice Age delayed over England, but finally it started to develop in the mountains and then spread to the lowlands, and the hippos found themselves stuck there. And then woolly mammoths and other cold climate animals came in there and they all died together. That's how I would explain it, by warm onshore flow. And Grayson also says, if the muskox required cold and the hippopotamus required warmth, and the stratigraphic evidence implied that they had coexisted, then a straightforward reading of all this information could imply that glacial climates had not, as most felt, been marked by severe winters, but had instead been equitable. In other words, there wasn't much contrast between winters and summers, exactly what we expect in this Ice Age model. So, there are lots of problems. Then at the end of only their last Ice Age, they had a mass extinction. Here are some of the numbers. They've varied a little bit. Like Africa, it's been a question, but these are the latest that I found. 100 species of large animals in North America over 100 pounds. That's 70% went extinct at the end of the Ice Age, the end of their last Ice Age. Europe and Asia, 40%. Australia lost 90%. Whoa, and South America, 80%. You know, the snow and ice wasn't really all that significant in Australia. In South America, it's mainly the Andes and Patagonia in the south. So that presents a lot of mysteries of why all this happened. By the way, I might add that these extinctions are only after their last ice age, which should, if we look between the lines, realize that, well, maybe there weren't any previous ice ages, of which they believe there are 49 of them now in the Pleistocene. Because you didn't have these extinctions after any other of their ice ages. So how would we explain it from the ice age? Well, first of all, as I showed in that diagram, winters would become eventually colder than today. And you had massive floods from catastrophic melting. You'd have more sea ice, cooler ocean temperatures, less evaporation, become drier, colder. Strong north-south temperature change still there. How? Well, the ice sheets are still there, and there might be melting, and the tropical areas have warmed up. So, between the subtropics and the middle and high latitudes, you have a strong north-south temperature difference, which results in strong winds, strong westerly winds aloft. So you have stronger winds, drier, so you have a lot of blowing sand and dust, which we have lots of evidence during the Ice Age of blowing sand and dust. Mainly lust that's over, a lot of it's in Siberia, and a lot of it's in the Midwest of the United States. Also, you'd have droughts and fire. I think a lot of times probably droughts and fire was why so many went extinct in Australia. And more permafrost, a lot further south. And you see this. And this would cause extinctions, and it probably varied from continent to continent, the real reasons, but they'd be combinations of these variables. Okay, I talked about the 5 Ice Age mysteries, which can be considered catastrophic, I suppose. But reasons why no post-flood catastrophes. And this, I'm getting into a controversial area. This has to do with the flood, post-flood boundary, which is debated. Here's my reasons for not believing it. The Ice Age would begin soon after the flood, starting in favorable areas because of all the dust and aerosols from the flood, and also meteorite impact like the Chicxulub in Mexico. You'd have a huge amount of particles reflecting sunlight back to space, causing much colder temperatures. Also, the Yellowstone supervolcanoes, which is a kind of an eroded stratovolcano, the ice built up over Yellowstone Park about 1,000 meters deep. And if those volcanoes were going off after the flood, now it took me 25 years to figure this out because I never knew the answer. It would have caused massive floods down the adjacent valleys if these volcanoes were going off during the Ice Age. But because there isn't any of that stuff, it appears that the Yellowstone volcanoes did not erupt after the flood. They erupted late in the flood. Also, I at once believed that the flood post-flood boundary was near the Cretaceous Tertiary or Cretaceous Paleogene level. But when I started to look at a lot of geology over the years, I discovered many anomalies with that idea. So Tim Clary and I have developed 35 criteria why we believe the flood post-flood boundary is in the late Cenozoic. Now, I find that it varies from place to place, and every place has to be evaluated on its own merits. So to me, I'd put the boundary in the Miocene, Pliocene, or Pleistocene, depending on the various areas, assuming the geological column. So this is kind of a postulate of where I think the ice occurred 50 years after the flood in areas far from the onshore flow of warm water, like in central Canada and the north central United States, and adjacent Europe. And then the high mountains. The high mountains would be glaciated 50 years after the flood. But much of Greenland would not be glaciated because of all the warm water and low altitude that would keep the glaciers away from there for a while. But as time went on, this is 100 years after the flood. Now these are just, these are postulated. That's based on basic meteorology during the Ice Age. So it expands. Hudson's Bay being too warm would not glaciate for a little while. And the mountains would increase. And in 200 years, then I finally think it really took off. And Greenland became glaciated by, within 200 years after the flood. So, it's because of that I don't believe there are huge post-flood catastrophes. Also, some of these 35 evidences, I will just showcase a few of them. And it's in all fields of geology and even in other fields besides geology. Sedimentary rock evidence. The Cenozoic has a huge volume of sedimentary rocks, and it's hard for me to understand how that can be post-flood. And here's some of the other reasons. Thick continental margin sediments. And anyway, here's a plot of the amount of sediments per period. And you can see the tertiary has more than any other period. So it's hard for me to believe that this can all occur after the flood. And it didn't seem to disrupt the progression of the Ice Age. For instance, the Los Angeles Basin is about 6,000 meters of Cenozoic strata. Santa Clara Valley, 6,000. The South Caspian Basin, which is about 500 miles in diameter, or kilometers, I can't remember. They have about 20,000 meters of Cenozoic strata. I find it very difficult to believe that these could accumulate after the flood. And then just recently, two of us have completed completed the early part of a research project. We're trying to figure out how much sediment were eroded off the continent during the recessional stage of the flood. And this GlobeSed project published their third version of the amount of sediments in the ocean. And here's a plot of that. You can see that up in this, the red area is over 15,000 meters. And the Arctic Ocean has a huge amount of sediment. And along the margins of the East Coast, the Gulf of Mexico, the Bay of Bengal. And of course, these were deposited mostly in the Cenozoic, I might add. I don't think they could be post-flood. But we did an estimate of how much we think that this was eroded from the flood. Since it's along the margin, we postulated that it was from flood runoff. So if you put it back up on the continents, all that sediment, we estimated that the amount of erosion over the Earth on the average was 1,900 meters. There's about 1,500 meters left, 1,500 to 1,800 meters. We're still figuring out that. So at the peak of the flood, you have about 3,500 meters of sediment that collected on the flood continents in about 150 years. That has a lot more to say. That we're still digesting all that, but the fact that you eroded off 1,900 meters on the average, this fits calculations I've made in various areas like Southwest Africa. And the Appalachians, I've done calculations of the amount of erosion. And here's a cross-section across the Atlantic where the sediments are mainly along the margin in deep basins. In fact, this cross-section shows that off the east coast of the United States, it's almost 15,000 meters of sediment. And then in Africa, off African coast, 1,500 meters. So it's along the edge, and practically all that was still in the continents at the peak of the flood that ran off. And then organic evidence. I'm only going to go into some of these. These are developed in the Journal of Creation and on my website in more detail if you need more evidence for all this. But I'll mention coal. This is the Wyodak coal seam in the Powder River Basin of Wyoming, northeast Wyoming and southeast Montana. Anyway, there are a number of coal seams there. They're from the Eocene. And as you look at other coal deposits of the Earth, 12 to 29% of coal is Cenozoic. I have trouble understanding if any coal forming after the flood. And the Powder River Basin, which I just showed that picture, has nearly pure coal seams around 100 kilometers long, 50 kilometers wide, and 75 meters deep, dated Eocene, which is early Cenozoic. But then there's Miocene coal in Hungary and Southeast Australia. So I'd have to put the boundary above this Miocene coal, assuming the geological column. And tectonic evidence. Much of the tectonics, the mountains going up, was during the Cenozoic. You had huge vertical tectonics, and you had tremendous horizontal plate movements during the Cenozoic and these other things. A new discovery is they're finding ultra-high pressure minerals in a lot of mountain areas, which us creationists need to really think about a lot more. This has a big message to tell us what the meaning of all these. And then a lot of geomorphological evidence. I mentioned the 1900 meters forming the continental shelf, rapid erosion of the continents, and water and wind gaps, and other things. And anyway, you look at the Colorado Plateau, it's about 130,000 square kilometers, or is it square miles? I can't remember. But anyway, the literature shows that this area has an average of 2,500 to 5,000 meters of erosion. This is what the secular scientists believe. And I believe it's true, because over Grand Canyon here, we know from the Grand Staircase that you had maybe 10,000 feet of strata over this whole area, depending on how thin the strata was there compared to the Grand Staircase, that was eroded. Now here's the San Rafael swell right in here. This is a dome that rose and was eroded. This is the Book and Roan Cliffs here, in here. And I did a calculation of the amount of erosion over the San Rafael swell. And based on trigonometry, I got 4,200 to 5,100 meters, which is close to what they consider the average. And you might notice that the top formation is the Green River Formation. This is one reason, not of many, that I don't believe the Green River Formation is from a post-flood lake. If anyone wants to ask me or any questions on that, I'll be glad to answer. But anyway, you had that huge amount of erosion over the San Rafael swell, which is exactly what you would expect during flood runoff. And then you have all these erosional remnants formed in the Cenozoic. This is Devil's Tower in northeast Wyoming. It's believed to be the throat of a volcano, about 1,200 feet tall, about 1,000 feet wide. And the lava was believed to be coming up into a volcano up in here. And the secular people think that you had sediments way up in here. And in the Cenozoic, something eroded all that sediment out. Yeah, the cursor shows up really well. Leaving that tower hanging there. But it's interesting that, you know, from a geomorphological point of view, steep slopes and vertical faces erode a lot faster than horizontal surfaces. So if it was uniformitarianism over millions of years, that couldn't stand. That would be eroded rapidly as all this sediment was eroded in the whole area. So there's There's thousands of these erosional remnants across the earth. Anyway, here's a water gap near where I live. I am looking west towards Yellowstone Park, which you can't see. This is Cody, Wyoming, and this is a water gap where the Shoshone River started in southeast Yellowstone, and supposedly if the river had anything to do with this, it should have went around this, because this ridge plunges down below the surface. And anyway, the Shoshone River ended up going right through here with straight east, cutting a water gap 2,500 feet, if the Shoshone River had anything to do with it, which I don't believe it did. I believe as the flood was draining, it channelized and carved these water and wind gaps, of which there's thousands of them across the earth. Also, there's climatic and miscellaneous evidence. There's a lot of warm climate fossils in mid and high latitudes. Lots of them. Way too warm to, I would say, be post-flood. Also, with all that volcanism and impacts during the flood, you'd have volcanic and impact winters. So you're going to have a lot of cooler temperatures that would jumpstart the ice age. And here's one that Clary has developed, the Whopper sand in the Gulf of Mexico during the Cenozoic. Something had to take it way out in the Gulf of Mexico as a sheet of sand. Anyway, there's 35 of these. We've developed them on other, in the literature. You can take a look at them. Here's a schematic that would remind you of the warm climate fossils in the northern Queen Elizabeth Islands. Swamp cypress, for instance, are found in the Queen Elizabeth Islands, dated Eocene. So you have a lot of lemurs, I'm not pronouncing it right, lemurs, are found as animal fossils. So you have a lot of this that's Cenozoic. So anyway, this is a controversial area. I recognize that. And at the International Conference on Creation, there's going to be a workshop with people from all positions that are going to discuss this issue. And you know, I think it's kind of like the blind man and the elephant illustration. They all come to different conclusions because of their background. And when we discuss these things, we always need to be charitable to people that have different views. And I'm willing to discuss any of it with anyone. But so in summary, at the end of the flood, you had catastrophic floods, catastrophic melting. It melted pretty fast. We also have good solutions for why woolly mammoths lived in the far north, why the lowlands of Alaska and Siberia were unglaciated, for wet deserts, for disharmonious associations, and end ice age mass extinctions. And there's 35 geological and climatological reasons why I don't believe there's any post-flood catastrophes. And I thank you